Polytec, advancing measurements by light.
So today I would like to introduce to you the scanning laser vibrometer of Polytec, and I would like to start with some parts of the system of which it consists. First of all, we have the electronic unit here in a roadshow case for easy transportation and shipment. So it consists of three components. On the top we have the junction box for connecting external signals and for triggering and signal output. We have the Vibrometer controller below that. That's the core of the decoding of the laser interferometer signals, and on the bottom line we have a high quality industrial data management system, which is an industrial PC, which is running the PSV software and the consisting software for displaying and for measurement. So the electronic unit consists also of a high quality TFT monitor with for display and analysis and for its setup. And the core of the system is the scanning laser vibrometer head. This is consisting of an interferometer, a built-in video camera, and a high quality, high precision scanning unit, which allows for deflecting the laser beam to the object on certain parts of the object. This is simply set up on a tripod here, which is the most convenient way to move it around to have a quick setup. The connection between the setup, the head and the electronic unit is a simple umbilical, which is easy to connect and to store. To start a measurement, you simply set up the measurement head, the scanning head, in front of the object at a distance between 80 millimeters and up to 30 meters. You see the same object here in the video image, so you see the laser spot in the middle as you would see it on the measurement object. After the setup of this test object and of the measurement head, we will start with a procedure to start a scan. For that we have to define scan points, which will now be done in the software. So there are various tools available to define the scan grid. It's a simple drawing procedure. This drawing procedure is done with mouse. You can choose different shapes, point densities, you can extract or you can add point densities within the object, so there's a high variety of point definition. And depending on the object you can also turn the object. You can have circular objects or just arbitrary shapes to create a grid which is sufficient. There are also grid coarsening and grid refinement tools available in order to create easily templates for grids which absolutely fit to the object. So after the grid definition is finished, the scan can immediately start. This will be directly stored on the 1 terabyte hard disk. The integrated signal generator generates now an excitation signal for an electrodynamic shaker or other excitation means, and while that the scan automatically proceeds. In the lower part the analyzer shows the results for each point. We'll now have a look for the scan process, how it looks on the object itself. So you can see, the laser point automatically scans through the object. The time, the elapsed time and the remaining time is displayed in the software, and after a short while the scan has ended. The scanning time depends mainly on the sampling time. For lower frequencies, the scan rate for the scanners goes up to roughly 30 to 50 points per second. So the scan speed is only defined by the sampling rate and the number of averages. The quality of the scan point signal to noise ratio is indicated by a color mapping. So we can see the color code here. Everything is in light green except some parts in the lower end which are green, which is a good value, and the other ones are optimal. An automatic remeasure function will correct for this if required. So the scan is now finished and we proceed to the analysis. What was acquired was the frequency response functions of each point automatically and the excitation signal. So the frequency response mapping over the whole object is now displayed as a deflection shape, as an operational deflection shape. This is the deflection shape as you can see it for a certain frequency, which is now animated. And you can simply pick other peaks in order to show the deflection shapes on other objects. What is also very helpful for documentation purpose is that you can overlay the video image of the object, and so you can see the object in the background, and it's also possible to use the shape and the skin of the object to display a deflection shape which is not color coded but where you only see the deflections of the object itself, and thus you can choose various kinds. We will have a closer look on that. Various kinds of deflection shapes. Now you see only the object moving and the measurement grid. So there are various types of interpretation. Everything which is measured can of course be exported in standard formats, as for example universal file format or simple ASCII format, and can also export it into emiscope format for further modal analysis. So these are the options which are available. We have a closer look on that as well. So these are the options to export. Also wave sound, wave data and wave files are possible. So now that's how a scan is done with the scanning laser vibrometer PSV 400. The Polytec scanning laser vibrometer is not only capable to measure large objects at low frequencies, but also samples at high frequencies. So the system is capable here of measurements up to 40 kilohertz. What you see here is a sonotrode for ultrasonic welding, and we want to measure the top surface, so the active surface of this object. For that we have set up the laser vibrometer in another way, so just pointing downwards onto the object so that we have optical access to it. Now we show how the scan looks like with the system. It's high frequency, sampling times are very short, so we can make use of the highest scan speed of the system. Okay, we will now start the scan, and if you look at the laser beam, you will see that it starts now moving. The excitation is broadband at high frequency, so you cannot hear the excitation, and the laser samples now the surface in 14 seconds completely. Scan is finished. I will now have a look for the results. So we see now this surface like before in the video image. And we switch now to the presentation mode, which shows us the deflection shape. We'll look for the right frequencies in the analyzer. And at the proposed resonance frequency of 20 kHz, we see that the object has a clear and very even out-of-plane motion, which is necessary for a good welding process. So PSV scanning laser vibrometer has now verified the functionality and operation of this sonotrode in a very easy way. So besides the measurement of the wanted frequency, you can also have a look at the operational deflection shapes at different frequencies which are not intended. So we see different deflection shapes at different frequencies. We switch now to higher frequencies. We are now in the 34 kHz range. We see clear higher order bending modes which are easily acquired. You can see the analyzer and the higher frequency mode. It's clearly seen with very low noise and without any surface preparation at the sonotrode surface. This short introduction to the Polytec scanning laser vibrometer PSV 400 shows its capabilities, its ease of operation, and its capability really to make life for the R&D engineer easier. Polytec scanning vibrometers, the gold standard in scanning vibrometry.
Polytec, advancing measurements by light.